Hypothalamus Artificial Intelligence, HI. Engineering projects for companies in the process of digital transformation. It presents its solutions and professional services based on decision-making artificial intelligence. Designed to optimize planning and operation in organizations in the electric and gas sector, using MMaaS mathematical models as a services. Hypothalamus Artificial Intelligence, HAI, has established a strategic alliance with IBM TD SYNNEX in Clearwater, USA, positioning itself as a key global partner. This presentation focuses on the services offered through HI Power, for the electricity and gas economic sectors. HI integrates its OPTEX technology, optimization expert system, IBM technologies, watsonx, decision optimization and C-PLEX optimization studio, and TD SYNNEX services. On the other hand, HI uses General Algebraic Modeling System, GAMS, as its programming language. Hypothalamus Artificial Intelligence, HAI, has established a strategic alliance with IBM TD SYNNEX in Clearwater, USA, positioning itself as a key global partner. This presentation focuses on the services offered through HI Power, for the electricity and gas economic sectors. HI integrates its OPTEX technology, optimization expert system, IBM technologies, watsonx, decision optimization and C-PLEX optimization studio, and TD SYNNEX services. On the other hand, HI uses General Algebraic Modeling System, GAMS, as its programming language. The models and services offered by HI are aimed at supporting the decisions of companies and organizations in the electricity sector, either through simple mathematical models, traditional decision support systems, and/or business artificial brains. These include optimization of dispatch of electricity and gas systems and markets, energy trading and risk management, energy efficiency optimization, evaluation of energy projects, smart grid optimization, regulatory affairs modeling, and electrical asset maintenance. The image presents what could be the decision support system of a generator, which follows the principles of enterprise-wide optimization, whose architecture is conceived as composed of multiple models of different types. Predictive artificial intelligence, advanced probabilistic models, synthetic generation of hydroclimatic variables, state estimation with the dual Kalman filter, and ARIMA-GARCH statistical models of spot prices. Interconnected system simulation model. Regulated economic dispatch. Optimization models. Robust supply chain design. Optimization of asset maintenance. ETRM, energy trading and risk management, and economic dispatch and unit commitment. Optimization of dispatch of electricity and gas systems and markets. HI Power is a decision support system that has been developed to support the decision-making processes of agents participating in the electricity and/or natural gas markets. HI Power is composed of a set of optimization models that describe the supply/demand process of electricity and natural gas. From this point of view, it determines the partial equilibrium point of the electricity and gas markets under conditions of economic efficiency. To develop, implement and maintain HI Power, is used OPTEX, Optimization Expert System, that it is the artificial intelligence created by HI that makes enterprise-wide optimization systems for the entire company. HI Power is built following the principles of structured mathematical modeling, which are specific to OPTEX. Under this conception, software is built by means of layers of equations, which are integrated to build the models, which are part of a decision support system. In the case of HI Power, it is an economic dispatch model, typical of the electricity sector. The diagram shows 8 of the many models available at HI Power. Any of the models can be run in their deterministic or stochastic version, making use of asynchronous parallel optimization. HI Power is built following the principles of structured mathematical modeling, which are specific to OPTEX. Under this conception, software is built by means of layers of equations, which are integrated to build the models, which are part of a decision support system. In the case of HI Power, it is an economic dispatch model, typical of the electricity sector. The diagram shows 8 of the many models available at HI Power. Any of the models can be run in their deterministic or stochastic version, making use of asynchronous parallel optimization. A well-known use of the high power is the ModPlan model. Implemented for COS-SYNNEX, the ISO of the Zine, used it for the planning of the expansion of the transmission system of Peru. ModPlan has been operational since 2014. Energy trading and risk management. Energy trading and risk management. According to Peter Bernstein, in his book, Against the Gods, The Remarkable Story of Risk, the revolutionary idea that defines the boundary between modern times and the past is mastery of risk management, the notion that the future is more than a whim of the gods and that men and women are not passive before nature. The essence of risk management lies in maximizing the areas where we have some control over the outcome, while minimizing the areas over which we have no control and the link between cause and effect is unknown. Energy trading and risk management, ETRM, corresponds to a function in companies that carry out energy trading activities, which inevitably require scientific management of financial risks. High ETRM corresponds to a set of mathematical models intended to support the decisions of the different agents involved in energy supply chains. It is made up of the following models: long-term stochastic optimization of energy trading, integrated electricity-gas dispatch, intended for the determination of spot prices in an electricity and gas market, using technical economic models that simulate the electricity market, and/or the gas market, and statistical projection of spot prices using Armax-Garch methodologies taking as references historical series of the spot price. ETMR mathematical models include financial risk coverage, multi-criteria optimization, and value at risk, VAR, analysis. The main result is the expected revenue, or cost, versus risk curve. As shown in the figure. Energy efficiency optimization. High EEO, energy efficiency optimization, is made up of multiple mathematical models which together support solutions in different aspects of energy efficiency in industries. The objective is to minimize the costs of energy consumption, or the energy used, and to control emissions, or any other pollutant. The solutions are grouped into two groups according to the type of industry, for example. Heavy industry, which includes the following industries: chemical, petrochemical, steel mills, steel, mining, metallurgy, and large manufacturing industries. Oil sector, production, refining and/or transportation of crude oil and refined products, and buildings, such as shopping malls, offices, residential complexes, universities, etc. In the industrial environment, mathematical models of energy efficiency include modeling of industrial processes, which are the ones that generate energy demand, and models of energy supply, mainly electricity and fossil fuels. The diagram presents an example of how energy of different types is consumed throughout the cement production chain. Energy project evaluation. The energy market is changing rapidly. When evaluating a project, many aspects, or alternatives, must be considered, for example, smart grids plus distributed generation plus new unconventional sources plus supply of thermal fuels plus interconnections plus smart equipment plus energy storage plus demand response plus. Hydroclimatic risk is decisive in the electricity market, which is greater if exposure to the risk of fuel prices is considered. The legal and regulatory framework, which offers new possibilities for self-generation, cogeneration and its marketing, is changing, which generates regulatory risk. Since the end of the last century, HI's mathematical models have been used to evaluate multiple energy projects, which has become a methodical and science-based process that guarantees the investor an accurate assessment of the economic value of the project, in terms of the revenue distribution function and its volatility. The process to follow is: high power optimize the dispatch and the market of electricity and natural gas, to be able to simulate multiple random scenarios that may be faced in the future. The high power results are synthetic series, for the entire planning horizon, dispatch of production units and spot prices. High ESOFIN, a financial model, evaluates in detail all the income and operational expenses derived from the energy market. Based on this model, typical financial statements can be evaluated. Balance. income statement, and cash flow. Finally, in mathematical models, financial risk management equations must be included to produce efficient risk versus income curves. From this process, decision makers have the necessary information to make a robust decision, according to their position with respect to risk. The first work carried out using this methodology dates back to 1998, when high models were used for the planning of the exploitation of a natural gas field in South America. Smart grid optimization. Smart grids are the future of the electricity sector. Its impact is of immeasurable dimensions, considering the impact of the Internet. Smart metering measurement systems are the way to collect large volumes of information, big data, necessary to capture the added value of this new dimension. Demand has become an active agent, leaving aside the passive position it has maintained until now. The mathematical models used to optimize large power grids need to be revised considering this new environment. High SGO, Smart Grids Optimization, corresponds to a set of mathematical models aimed at supporting the decisions of the agents participating in smart grids. It is made up of the following models: optimization of demand response, optimization of electrical energy management in building complexes, such as universities, housing estates, shopping centers, etc. Optimization of energy efficiency, optimization of electrical energy management in industrial systems intensive in energy consumption. Projection of availability of renewable energy sources, short/medium-term prediction of the availability of renewable energy sources, such as wind, solar radiation and water resources. Load management optimization, electrical load management optimization. Phase balancing and voltage management. Distribution network planning, optimization of the design of smart grids of the operation, based on its reconfiguration. Electricity theft detection, electricity network fraud detection systems, and real-time optimization, advanced control systems for optimizing the operation of a smart grid. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. Regulatory affairs modeling. Hypothalamus artificial intelligence, HI. Engineering projects for companies in the process of digital transformation. It presents its solutions and professional services based on decision-making artificial intelligence. Designed to optimize planning and operation in organizations in the electric and gas sector, using MMaaS mathematical models as a services. The advent of new energy sources, such as solar, wind, green and blue hydrogen. These sources are directly involved in the assessment of the impact on climate change and are usually associated with energy transition processes. Certainly, at the end of the production chain, new sources reduce CO2 and NOx emissions, a perception that can change if the entire cost of supply, including all the activities involved, is considered from the point of view of costs and emissions. Evaluating them accurately involves a greater effort in mathematical modeling. If the second aspect, the supply of electric batteries, is considered, the situation may be different. The battery production process involves the exploitation of special minerals, lithium, cobalt, zinc, magnesium. Its cost and emission of CO2 and NOx includes location, exploitation, transport and industrial refining. When the battery reaches the end of its useful life, its disposal is an issue that must be included, since it can include the development of specialized plants in this business. The cost of a battery for a car is high, and in many cases the relationship of the battery with the brand generates undesirable dependencies in a competitive market. These accounts should include accurately assessing the social, environmental, and economic sustainability of the project. It is possible that, when considering all accounts, including all the supply chains of all resources, the project is not profitable, and/or it is not environmentally sustainable, because it generates more pollution than it avoids. Electrical asset maintenance. Interconnected systems maintenance. Holistic planning is understood as the integrated planning of the largest installations of the electricity system. These can be power plants and/or generation units, energy storage, conduction channels, reservoirs, transmission lines, and transmission system substations. To analyze the above, a model can be generated that integrates the economic dispatch, or any subsequent modifications, with the maintenance model, equations that represent the maintenance process for each type of installation. The objective of the operation will be to maximize the social surplus, which for electricity systems in which an inelastic demand is assumed, corresponds to minimizing operating costs. Below are the results of a realistic example case. In these results it is possible to visualize the coordination of the maintenance of the largest generation plants of the interconnected system. Below are the results of a realistic case study. In these results, it is possible to visualize the coordination of the maintenance of the largest generation plants of the Colombian interconnected system. As a result of the optimization model, the figure shows the availability of the generation plants, for each period of the planning horizon. Electrical asset maintenance. Case: solar power plants. Energy availability and demand introduce many uncertainties into the operation of low-carbon power grids. One way to address these uncertainties in network operation is to develop an accurate forecasting algorithm. Topic areas in supply/demand modeling in solar farms include availability of renewable sources, e.g., wind and solar, demand forecasting and demand pooling, and rule of active ingredients, solar cell groups. It should be borne in mind that all these issues are part of the problem and that, if all of them are not solved, the decisions taken do not have to be optimal and can lead to undesirable consequences. Below is an example of how AI can be leveraged to solve PV prediction tasks following the model proposed by Yang et al. To predict solar irradiance on a farm during the K+1 period. An example is referenced where AI can be leveraged to solve tasks such as photovoltaic prediction, following the model proposed by Yang et al. To predict solar irradiance on a farm during the period K+X, and allocation of maintenance resources, using a mathematical optimization model. The figure shows the geographic locations of the target solar farm, C6, and N neighboring solar farms. The result is a scheduling of resources to attend to maintenance work, in all solar plants, during the planning period or during a fixed cycle of maintenance activities. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.